Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are revising fluid mechanics. In the first part of weeks, we have already covered fluid statics and here we are covering fluid dynamics now. In the previous class, we introduced the concept of Bernoullis Principle. And in today's class, we are going to look at several applications of Bernoullis Principle. Okay, so without losing any further time, let's share our screen. So here we go. So before starting for the application of Bernoullis principle, let's look into the expression of Bernoullis principle once again. So Bernoullis principle, and you must always understand that it is applicable for laminar, incompressible, non-viscous, homogeneous fluid, you can say. Okay, and the flow must be laminar, or also you can say irrotational, it must be. Okay, so these are the criterions, okay, under which we will be applying Bernoullis principle. And the statement is, as the liquid flows from one position to another position, so P plus rho GH plus half rho V square, this term is going to remain constant. Okay, and we have looked that this expression is nothing but a form of principle of conservation of energy. Looking at it that way, like this term is nothing but kinetic energy per unit volume of the liquid, and this term is nothing but gravitational potential energy per unit volume of the liquid, and this term over here can be termed as pressure energy per unit volume of the liquid. It is very convenient to look at the changes in terms of change in energy, because that way we can say, like, if some form of energy is increasing, that must be decreasing at the cost of some other form of energy. Okay, because here the principle of conservation of energy is applicable. Bernoulli's principle is nothing but a form of principle of conservation of energy. So now we are ready to look into some application of Bernoulli's principle. And very first application we are going to look at it is something called speed of efflux. Okay, speed of efflux. Okay, so let's, for example, imagine that there is a container of wide base. Wide base means like its cross-sectional area is large, and some liquid, some ideal liquid, that means incompressible and non-viscous, some ideal liquid is filled in this container. Okay, so right now it is static, but what we have done over here, like we have made an orifice, very small orifice over here. Like the orifice is such that, like, the area of container, let's say, is A1, cross-sectional area of container is A1, and A2 is the cross-sectional area of this orifice. So size of the orifice is small, so we can say that A2 is much less than A1. So this is the thing, like when we are saying that we have put a orifice, that is what we mean. Okay, so when we will be putting a orifice over here, so over this point here we have exposed the liquid to the atmosphere. So liquid will start coming out from this orifice with certain velocity, and we here are interested in finding out this velocity, and this velocity would be known as velocity of efflux. Okay, so for example, let's say this is v2, the speed is v2 over here, and v we need to find out. Okay, so you might be already knowing the expression of it, like this is nothing but root 2gh, where h is the depth of orifice from the open surface of the liquid. Okay, this equation all of you might be already knowing, but let's say how we have got this. Let's try to revise that concept. Okay, so in order to do that, in order to apply Bernoullis principle over here, we need to choose 2 points. Let's say one point we will be choosing over here, and another point of liquid we would be choosing over here. Okay, and we will be applying Bernoullis principle between these 2 points, 1 and 2, which is located inside this liquid, homogeneous liquid over here. So the idea we are looking at is like we are going to apply P1 plus rho g h1 plus half rho v1 square is equal to P2 plus rho g h2 plus half rho v2 square. So we are very carefully going to write each and every term involved in this equation now. And looking in terms of energy also, you can say, like when the liquid will be coming out from here to here. Okay, so from this point to this point, just inside the orifice, we can say that the gravitational potential energy is decreasing. Gravitational potential energy is decreasing, okay, due to which pressure energy would be increasing. And as the liquid moves in to out, that pressure energy is going to convert into the kinetic energy of the liquid, and that is why this liquid is going to come out with some efflux velocity. Okay, so here we must realize that P1, okay, is nothing but the atmospheric pressure. The pressure at point 1 would be nothing but atmospheric pressure. And let's develop a habit of working in terms of gauge pressure, because here in this equation, when we are writing this equation, mostly we are looking in terms of pressure difference. Okay, so pressure difference, if we are looking at, so it is always convenient to work in terms of gauge pressure, because the atmospheric pressure will anyway cancel out in the expression of P1 and P2. So the gauge pressure at 1 is going to be equal to 0. Okay, and see this, let's say this level of height is, let's say h2 is equal to 0 reference we have assigned. In that case, h1 will be equal to uh, plus h, you can say. So this would be rho g h plus half rho v1 square, you can write. And the gauge pressure at point 2, since point 2 has been exposed to the atmosphere also, the gauge pressure here will also be equal to 0. h2 we have assigned as reference, so that is also 0, and that is half rho v2 square, you can say. So here what we will be able to rearrange this equation, that would be half rho v2 square minus v1 square is equal to rho gh. Now it's time to use that relationship. A2 is much less than A1, and also from principle of continuity we know that A1 V1 is equal to A2 V2. So V2 can be written as A1 by A2, or simply V1 can be written as A2 by A1 into V2. So if we substitute this value over here, so what we are likely to get is half rho, and V2 square we will take common, and that would be 1 minus, that would be A2 square by A1 square over here, which will be equal to rho gh. And since A2 is much smaller than A1, this quantity here would be negligible. So this quantity here will be approximately equal to 1. So just by rearranging, rho will anyway get cancelled both sides. So V2 we will be getting it as root under 2gh. So this is the velocity of efflux, let's just simply say v. Okay, and here this velocity of efflux will depend upon the fact that at what depth this orifice is from the open surface of the liquid. This is the open surface of the liquid, and this is the position of orifice. So this small h is representing the depth of orifice from the open surface of liquid over here. Okay, and definitely it is not going to depend upon the density of the liquid. Okay, so this is velocity of efflux. Let's look more closely into this situation, and let's look at other aspect of this problem. Okay, and here we want to look at something like a range and time of flight. So for example, if this is a container, and let's say liquid is filled in this container up to brim. Okay, and this container is kept over a horizontal surface, let's say, and let's say height of the container is h, and we have made some orifice here of very small cross sectional area in comparison to the cross sectional area of the container, and this is at depth h from the open surface. So obviously we understand the velocity of efflux over here is going to be root 2gh. So if the orifice is made such that the jet of this liquid is going to come horizontally at this point, so this jet of liquid will follow a path which would be parabolic, because it will be moving under the influence of gravity, so the motion will be projectile. Okay, so this jet of liquid is going to hit this ground somewhere here. Okay, and let's say this is x, which is horizontal range over here. Okay, so we want to find out the value of x. Okay, so in that case you must realize, like, if this orifice is at depth h, okay, it must be at a height capital H minus h from the bottom over here. So in that case, the time of flight, if we want to find out like how much time that an element of liquid is going to take to reach from this position to this position, so this is simply going to be 2 times capital H minus h by g root under. So this is time of flight. So obviously if we consider if you want to find out the horizontal range x over here, we need to consider the motion along horizontal direction, which would be uniform motion. So you must realize that it is going to be equal to component of velocity along horizontal direction, which is going to be equal to u is equal to root 2gh multiplied with the time of flight. So that would be root 2gh multiplied with 2 times capital H minus h by g root under. Okay, so g obviously is going to get cancelled over here, and you will be left up with this quantity. Okay, so here this is the horizontal range. We want to investigate further this equation. See, this horizontal range, okay, you must realize is a function of small h. If you increase if the small h is very, like, if small h is 0, means if the orifice is somewhere at the top, then you must realize that velocity of efflux will be 0. Okay, so the range will be 0 over here. And if we look at the other extreme, let's say for example, if small h is equal to capital H, means if the orifice is at the bottom of the container, although the speed of efflux would be maximum, but this quantity time of flight will be 0. In that case also x is equal to 0. So as we go, as the position of orifice is uh, lowered from the open surface of the liquid, okay, you can say the range would be increasing from 0, and it will reach to some maxima, and then again it will start decreasing, okay, as the position of orifice is lowered, and when it is at the lowermost point, the range will again become 0. So in that case, if it is increasing to some maximum value, we will be looking, we will try to find out what would be that maximum value. So we must have a condition for x to be maximum, you can say. Definitely looking at this function, you should realize whenever this quantity and this quantity is going to be equal to gonna be equal, then we can say at that situation x will be maximum, or you can use maxima minima over that function to get small h will be equal to h by 2. So at small h equal to h by 2, the range is going to be maxima, and r will be equal to us, or simply x max will be equal to, you can say, when you substitute this value in this equation over here, you are going to get x max is equal to h. So that is one thing you need to understand. Another aspect of this problem here is, you must realize, let's say, something called time of emptying. Let's say this is the container, okay, and this is completely filled. Let's say height of container is capital H, and it is completely filled with liquid. And let's say cross sectional area of the container is A1, and cross sectional area of this orifice here we have made at the bottom, and A2 is definitely much less than A1. So obviously the liquid is going to come out from here. Okay, so if we do not do something externally to maintain the level of the liquid in the container, definitely level of the liquid in this container is gonna go down, because here the liquid is continuously coming out. Okay, so here after some time we are definitely going to look at a situation when this container will become empty. Okay, and we are looking to find out the time of emptying. Okay, so how are we going to do that? So for that, let's imagine, so at any time, at say at t is equal to t, okay, see, this level of the liquid will be variable, it will be coming down. So at t is equal to t, let's say instantaneous height of the liquid, open surface of the liquid from the bottom is h. Okay, so this liquid, this level is basically coming down. Let's say this is 0.1, so let's say this is coming down with velocity v1, and the liquid at this instant will be coming out from over here, and at this instant you can say the depth of orifice from the open surface is only small h, so v2 is going to be equal to root 2gh. Notice that v2 here is variable as well. So now applying a principle of continuity, between point 1 or cross sectional area 1 and cross sectional area 2, we can definitely say a1 v1 is equal to a2 v2 over here. So a1 and v1, you must realize that is nothing but the rate of decrease of small h. So v1 you can write it as minus dh by dt. So let's substitute that value over here. That would be minus dh by dt into a2 times, and v2 you can see that is nothing but root 2gh. Okay, so this is a differential equation in h and t, and let's make it in variable separable form. So that would be dh divided by root 2gh is equal to minus a2 by a1 into dt, and when we will be integrating both sides. Okay, so let's say we have started from t is equal to 0, and we are looking to find out the time of emptying, let's say capital T, and the level of the liquid which was initially h, and the final level we are looking at is 0. Okay, so solving this differential equation over here, you will be getting t is equal to a1 by a2 times root under 2h by g. Okay, so the thing I want you to notice over here is t here is directly proportional to root h. Okay, so from this information, one another type of problem could be dealt up with. Like for example, this is the time to empty the complete container. Okay, and if we want to find out the time to half empty the container, means I want the time taken, like from the level to become h to h by 2, how much time it will take, we are interested in finding out. So we can use this proportionality over here. So like for example, from h to 0, the time taken is t. So from h by 2 to 0, the time taken would be, using this proportionality, okay, you can say this would be t is directly proportional to root h, and we are trying to empty the half filled container. So this is going to be, you can say, t by root 2 over here. Okay, so in that case, from h to 0 it is taking this much time, and h by 2 to 0 it is taking this much time. So definitely from this you can say t will be equal to, small t will be equal to capital T minus t by root 2, or you can say 1 minus 1 by root 2 times t, and the value of t we have already calculated, that is a1 by a2 into root under 2h by g over here. So this was one variation. Okay, another variation in this same similar problem is there will be recoil of the tank, or you can say a recoiling tank problem. Okay, so let's say this is the same tank we are looking at. Okay, and let's say this is kept at a smooth horizontal surface. Okay, and here we have put up an orifice. Okay, obviously its area is much smaller. Let's say the area over here is a1 and the area over here is a2. Okay, and initially some liquid is filled in it. Okay, so this problem is regarding, like, if the liquid is going to come out from here. Okay, so the liquid will exert a thrust force on this system in backward direction, this F. Okay, there would be some thrust force, and this force would be given by, we have already looked at this, that the outgoing liquid will be exerting force in opposite direction, and that is going to be rho av square. So it is coming out of this cross section, so rho a2 into this v square, you can say. Okay, and please remember, this v is variable. V is equal to root 2gh, where h is the instantaneous value of the depth of this orifice from the open container, open surface of the container. So in order to, like, the problem statement is here that assuming mass of empty tank is negligible, okay, we have to find the speed of the tank when it gets completely emptied. Okay, so obviously it is going to take some time to get empty, and what time that would be we have already found out. So uh, like, what we have to find out at that instant when it has become completely emptied, okay, what would be its velocity? It will be obviously recoiling in backward direction, you can say, due to the influence of this force over here. So we want to find out that quantity over here. So in order to do that, like, see, this is the force we have calculated. So let's write the expression for force. So that is rho into a2, and let's say at any instant the height of the open surface is h. So this is going to be, v is going to be root 2gh. So in that case, this quantity would be simply root 2gh square over here, which is 2gh. So in that case, if we wish to find out the acceleration, so acceleration is going to be force upon the mass of the system, and we have already said that the mass of the tank is negligible. So whatever mass we are looking at is the mass of liquid which is at that instant present in the container. So force is rho A2 into 2gh, and the mass definitely would be density of the liquid times volume of the liquid. So volume of the liquid would be the cross sectional area of container, that is A1, times the instantaneous height h. So A2 will not cancel, h will get cancelled over here, and this rho will get cancelled over here. So what you will be getting is 2A2 by A1 times g, and that is a wonderful result, because you can see that this term is a constant. Okay, this term is constant, so the motion of this container would be an uniformly accelerated motion. And being said that, finding out the final velocity becomes very, very easy for us. So v is going to be simply the acceleration times t. So this is the final velocity, so v is going to be acceleration times t. So acceleration, we have already got 2a2 by a1 into g, and the time of flight we have already found out in the previous example, and that was equal to a1 by a2 into root under 2h by g over here. So you can see that this a2 will get cancelled, and this a1 will also get cancelled, and you will be finally getting this as answer, 2 times root under 2gh. So this was one more example. And let's take another variation of this problem. Let's say, for example, this time we are having a container, okay, and we have several immiscible liquids filled in this container. Let's say this liquid is of density rho 1, this is of density rho 2, and this is of density rho 3, etc. And height, this height is h1, this height is h2, and this height is h3, etc. Okay, and we have made some small orifice over here, so liquid is going to come out from here, and this velocity we want to find out. Okay, this velocity we want to find out. So obviously we are going to apply Bernoullis principle over here. So in order to apply Bernoullis principle, we need to choose 2 points inside the liquid. Okay, so where we are going to choose that point? Can we choose 1 point here at the open surface and 1 point here? So no, we cannot do that, because this point here is located in a liquid of density rho 1, and this point here is located in the liquid of density rho 3. And as we said earlier, that the Bernoullis principle will be applicable in a homogeneous liquid, means density we want to be same throughout. So we need to choose 2 points, okay, where we are having same liquid. So the best idea would be to choose 1 point at this interface. Let's choose 1 point A over here, the another point B over here, and let's apply Bernoullis principle between these 2 points. And in order to do that, like the pressure at A you can write very easily. Okay, like pressure at A is going to be, I'm going to write the gauge pressure, so that would be going to rho 1 gh1 plus rho 2 gh2, and the gauge pressure at B is going to be equal to 0. So when we will be applying Bernoullis principle, that is PA plus rho GHA plus half rho VA square will be equal to PB plus rho GHB plus half rho VB square. You must realize that like a rho we will be using, like we are working in the liquid of density rho 3, so this rho is going to be rho 3 everywhere. Okay, and this if we choose that level as a reference, so HB is equal to 0, so HA will be equal to, you must realize, that will be equal to H3 over here. So this HA, so this term will be 0, and this term here is going to be rho 3 GH3. Okay, and also you must realize that VB would be much greater than VA, because like the cross sectional area of orifice is greater than the cross sectional area of the open surface, or the surface a cross sectional area of container over here. So just by rearranging this, you are going to get the velocity at point B, or simply V, you can say, that will be equal to 2 times G multiplied with rho 1 H1 plus rho 2 H2 plus rho 3 H3, and that divided by rho 3. Okay, so this would be the velocity of a flux in this case. Okay, so we have looked at the limitation that we can work with Bernoullis principle in a homogeneous liquid. Okay, so now let's look at some other application of Bernoullis principle. Okay, let's look at another model, and this is the concept of siphoning, or you can say siphon tube. Okay, you might all have worked with the siphon tube. It is used to, okay, extract some liquid, okay, take out some liquid, okay, and only under the influence of gravity, with the help of gravity only. So let's say there is a container which is filled with some liquid over here, and we want to take out liquid. We want to maintain a flow of liquid from this container to outside. So what I will be doing is, I will siphon the system. I will put a siphon tube. Let's say that would be a thin tube. Pardon my bad drawing. Okay, so let's say this is something called siphon tube over here. Okay, so what we are going to do over here, we are going to suck the air out of it. So the liquid will start rising in it, and liquid will then start coming out of this end over here, this open end over here. Okay, and this flow will be maintained. Okay, and what are the condition for the siphon tube to work properly? Okay, we are going to look at that. Okay, so in order to do that, let's define some points. Okay, let's say, for example, let's just say point A, and let's say this point is B, and say there is some point, the topmost of the siphon tube, that is, let's say C, and let's take one point D over here, and let's say this open end is E. Okay, and say um, this level we have seen already. So let's say this is H1, and this is H2, and this is H3. So first thing we want to find out is, if the liquid is going to come out of here, what would be the velocity of this liquid over here. Okay, so all the parameters are given, and you have to also assume that this siphon tube is having a uniform cross-sectional area. Okay, so now see what exactly is happening. Let's look in terms of energy. Like, for example, when the chunk of liquid is going to move from A, or let's take one another point over here, some F, just outside the opening of this a siphon tube, but at the same level. So from A to F, the gravitational potential is increasing. Gravitational potential energy is increasing. Sorry, decreasing. So at the cost of which the pressure energy would be increasing. Okay, so here the pressure of the liquid is greater than that of A. But as the liquid enters from here to here, okay, now you must see, when it comes here, it will be gaining some velocity, it will gain some kinetic energy at the cost of this pressure energy. And as this liquid will rise in the siphon tube up to a level of C, for example, as it would be rising, okay, its kinetic energy is not gonna change. Its kinetic energy is not gonna change because the cross-sectional area of the siphon tube is uniform. So the V is going to be uniform at all those points. So as the liquid rises, you must realize the kinetic energy is not changing. Okay, So but you can see definitely gravitational potential energy is increasing, so it must be increasing at cost of something, and what that something is pressure energy. So as the liquid moves up, okay, the pressure or pressure energy per unit volume decreases, okay, and from here it again starts coming down. The kinetic energy is not changing for the liquid as long as it is moving inside this siphon tube, okay. So as it comes down, okay, its gravitational potential energy is again start decreasing, and the pressure energy increases, and finally when it comes here at this point over here, okay, uh, um, like its gravitational potential energy is minima, and the pressure energy again become equal to PATM. So we have looked at this situation qualitatively, and now let's look at this same problem quantitatively also. And you must also realize, like, the pressure at A here, the gauge pressure is 0 and the pressure at E is also 0. So between A and E there is no pressure difference. So if we apply the Bernoullis principle between point A and E, so we are going to get the velocity at point E is equal to root under 2g, and there would be some quantity in this bracket, and this bracket would be the difference in level of this point E and difference in level of this point A, and this quantity you can definitely see is equal to nothing but h1 plus h3. This is h1 and this is h3. So velocity of efflux is going to be root under 2g h1 root 2g h1 plus h3 over here. And like we said, like when the liquid will be rising in this siphon tube, the pressure would be decreasing, so obviously the pressure at point C would be minimum over here. So can we find out the pressure at point C? Okay, generally student commit mistakes. They think like pressure at point A, okay, is like atmospheric pressure. This is atmospheric pressure. So the pressure at point C using the pressure variation formula is going to be PATM minus rho GH2, etc. But that is not the case. You must realize, like here, the kinetic energy per unit volume is 0, but here kinetic energy per unit volume means half rho v squared term is not 0. So in order to do that, like to find out the pressure at point C, we must choose, like it would be convenient to choose 2 points where there would be no difference in kinetic energy per unit volume. For example, point C and point E. So the pressure at point E is atmospheric pressure, and the pressure at point C would be less than that. And how much would that be less than that? You can see, like here pressure is less, pressure is less and height is more. So here pressure will be more and height would be less. So PC here simply you can write, in comparison to this A, the pressure at E is PATM, you can say PATM, and uh, minus you can write that would be rho G, and this difference of level, so that is definitely going to be H1 plus H2 plus H3. And also you must notice, in order for the siphon tube to work properly, siphon tube to work properly, okay, this PC can never be negative. So this PC has to be greater than equal to 0. So that means, like, PATM must be greater than rho G H1 plus H2 plus H3, or you can say PATM by rho G must be greater than H1 plus H2 plus H3, or you can say this height got to be less than this quantity. It is not like you can have like any height of this siphon tube, any height of this point C. No, like this height, okay, this height and this height, the level of these two, the difference of level of these 2 points, which is h1 plus h2 plus h3, has to be less than p atm by rho g in order for this siphon tube to work properly. Okay, so that is one of the idea. And also you must realize, like if you put some hole over here, like let's say from hole over here, so what will happen? So whenever you put an orifice over here, you are exposing the liquid here to the atmosphere. So the pressure immediately will become zero over here. So you will not be able to pull the liquid out. And see, like here atmospheric pressure is there, here atmospheric pressure is there. So basically there would be no enough pressure energy in order to force this liquid to this height. So siphon tube will not work in that case as well. Okay, and now like in the very beginning I told you, let's for example look at this point F and this point B. Okay, so can you say that the pressure at point F and the pressure at point B, because they are at same level in the liquid, are same? The answer is no. The pressure at point F and point B are not same. You must realize, like the liquid at point F is moving with negligible velocity, but whereas the liquid at point B will be having velocity v over here. Okay, so now you see, so it has got some velocity or kinetic energy per unit volume. Okay, so that must be at the cost of the pressure energy. So the pressure at B will be less than that of pressure of F. The pressure of F would be greater than pressure at B. Okay, and the pressure at F, simply you can write by comparing these 2 points. So pressure at F is nothing but P atm plus, you can say, rho g uh, H1. And the pressure at B, when you will be writing pressure at B, what you need to work is like the Bernoullis principle between this B and E, because here the velocity is V, same kinetic energy per unit volume. So that is why we are comparing these 2 points over here. So that would be, here the pressure is P atm. So this is going to be P atm minus simply rho g h3 over here, you can say. So obviously you can see that the pressure at F is greater than pressure at B clearly. Okay, so this was the concept of siphon tube. So now let's move on to one another application of Bernoullis principle, and that is the concept of Pitot tube. Okay, Pitot tube is a device which is used to measure flow velocity in a pipe. Okay, so this is the idea. So let's say we have a pipe, okay, and we want to measure the flow velocity. So we will install some Pitot tube in it, and this is how the installment looks like. So we use a L shaped tube. Okay, and let's say the liquid here is flowing in this tube, okay, with some velocity v, and we want to measure this flow velocity. So this is the arrangement of a Pitot tube. So what will be happening when we install such a device? So since there would be some pressure over here that would be pushing liquid in this open column to some height, and there would be pressure over here and it will be pushing liquid in this column as well. So the way I have drawn, you can see that the height of the liquid, raised liquid, in the L column is greater than this column. Let's say this difference is basically equal to H. So this Pitot tube indicates this value of H, and then you can calibrate this instrument to give V is equal to root 2gh, and that will be giving you the value of the flow velocity. So how we have arrived at this result, that is the statement over here. So in order to answer that question, okay, let's imagine one point below this column, let's say that is point 1, and let's take one point just inside this. Okay, let's say this is point 2. Now you realize like the velocity of point 1 is going to be same as flow velocity, that is simply v. V1 is equal to v, and you can say at this point there is like, once this level of the liquid has reached this flow has there will be no longer the flow of liquid in upward direction. So this part of the liquid here has become stationary. So you can say the velocity at point 2, v1 is equal to v, but v2 is equal to 0. This part, this point is not moving at all. This part of the liquid is not moving at all, because the liquid is no longer rising in this column. Okay, so from the application of Bernoullis principle, here you can definitely see like v1 is greater than v2, because value of v1 is v and value of v2 is 0. So you can definitely say using Bernoullis principle, because p plus half rho v square is going to be constant in comparison of 1 and 2, because these points are at same height. So you can definitely say that P1 would be less than P2. So if the pressure here is less, and it is going to push the liquid in this column, it will push this liquid less, and here the pressure is more. So the liquid will be pushed to a greater height in this Pitot tube over here. So and this pressure difference P2 minus P1 could be measured using that Pitot tube, and let's say density of the liquid is rho, so that is going to be rho g h. And also you can apply Bernoullis principle between point 1 and 2. So P1, we will be writing P1, and there would be no h term because h term will be getting cancelled. P1 plus you can say half rho v1 square, which is v, is equal to P2. Okay, and there would be no rho gh term and no rho v square term, because v here is 0 over here. So simply you can see that half rho v square is nothing but P2 minus P1, and P2 minus P1 we have already measured, which is equal to rho gh, and this rho will get cancelled over here, and v you will be getting it as a root 2gh. So that is how we were able to measure the flow velocity, flow speed in this piping system using Pitot tube. There can be an alternate arrangement of Pitot tube also, which is useful if in the pipe the gas is flowing. In order to measure the gas flow velocity in the tube, we cannot use like this arrangement of Pitot tube, because here both of these columns are open. So if there is gas, that will start coming out of these columns over here. So this arrangement of Pitot tube is not useful in case of the flow of gas. So in order to do that, we use a different arrangement. Okay, but same working principle you see. So let's look at that arrangement as well. So that arrangement is, let's say this is the tube, and here the installment will look something like this. This is how the installment will look like. Okay, and in this Pitot tube here, some mercury is filled, or some denser liquid that is filled over here. Okay, so what will happen, let's analyze it first. Okay, so let's say this is point 1 and this here is point 2. As we have stated already, let's say the velocity of liquid at point 1 is going to be v, which we are intending to measure. But just inside it. So there would be no longer flow of the gas in this part over here. So V2 is going to be equal to 0. V1 is going to be equal to V, and V2 is going to be equal to 0. So obviously, if V1 is greater than V2, V1 is greater than V2. So like we said, P1 would be less than P2. So here the gas pressure will be less, here gas pressure would be more. So the gas will be pushing more in this L column. Okay, so the whatever liquid is here, let's say for mercury, it will push the right limb more, and here the push will be less. Okay, so since the push is more, so the liquid column will be down in this part, and let's say mercury column will be more in this part. Okay, and basically the Pitot tube measures the difference of height in these two limbs. So let's say that is equal to h over here. Okay, so just by measuring this h, we are willing to find out this v. Okay, so this, let's say this is a rho hg over here, like this is the mercury. So in order to do that, like, can we find now the pressure difference between point 2 and 1, P2 minus P1? So since we have used already this Pitot tube, so P2 minus P1 is simply going to be rho hg into g into h. That will be in case of gas. In case of gas. Okay, and if we are using some liquid over here, so this term here will be becoming, see, there would be, when we are finding out the pressure difference between these 2 points over here. So the pressure here and the pressure here will be, the pressure difference will be due to this liquid column as well. So this term will be rho hg minus rho into g into h. That is in case of liquid. Okay, and this rho is nothing but the density of the liquid. So please do understand, like, the pressure difference between point 1 and 2 in terms of this h over here will be simply rho hg into g into h. That is in case of gas, because gas does not really experience significant gravity over here, because like, see, the variation of pressure inside a gas does not depend upon the gravity, does not change due to height significantly. Okay, so in case of gas, this would be the simple formula of P2 minus P1, and in case of liquid, it is going to be this over here. So P2 minus P1 we have measured, and using Bernoullis principle between point 1 and 2, this P2 minus P1 is going to be equal to half rho v square. So half rho v square will be equal to this term. Okay, uh, in case of gas, and will be equal to this term in case of liquid over here. So let's equate this. So that would be equal to rho hg into g into h. So this here will be giving you v is equal to rho hg by rho into 2gh root under. And if we are using liquid here, so half rho v squared term will be equal to rho hg minus rho into gh. So in this case, we are going to get v is equal to rho hg minus rho upon rho into 2gh. So that is how a Venturi meter works. So there is another, sorry, this is Pitot tube. So another device we are going to look at is, you might have already guessed. Okay, so that is Venturi meter. Okay, Venturi meter is a device which is used to measure, that is used to measure volumetric flow rate, that is uh, volume of liquid per unit time flowing through the pipe, volumetric flow rate of fluid, let's say fluid in a pipe. Okay, and its arrangement is something like this. So let's say we have a pipe, and in between, in order to measure the volumetric flow rate, we install a Venturimeter, and this is how the installation looks like. Sorry, 1 second. Okay, this is how the installment looks like. Okay, so you can see that this installment basically tries to change the cross-sectional area. So let's say here the cross-sectional area below that limb is A1, and here the cross-sectional area is A2. As you can definitely see that A1 is greater than A2, that we can clearly see. So if liquid is flowing inside this tube, you must clearly see, let's say at this cross section velocity is v1 and at this cross section velocity is v2. So using principle of continuity, we can definitely say that v1 is going to be less than v2. So if the velocity is greater over here, so the pressure is going to be less. Okay, so the order of pressure is going to be p1 would be greater than p2. And you must realize, since the pressure is more over here, it is going to push the liquid in this limb to a greater height, with then the liquid is going to push the liquid in this limb. Okay, so there would be difference of level in these two limbs, and Venturimeter is going to measure that difference over here, and let's say this measurement is h. Okay, so obviously you must realize, so if the density of liquid is rho, so then this P1 minus P2 thing is going to be equal to rho GH. And applying Bernoullis principle between point 1 and 2, like P1 minus P2, you can write it as half rho times V2 square minus V1 square. And that is going to be equal to rho GH. And for example, we are interested in finding out V1 over here. Okay, so V2, we can write it as A1 V1 by A2. So when we will be substituting that thing, so that will become half rho V1 square into A1 square by A2 square minus 1. That will be equal to rho GH over here. So this row will definitely get cancelled, and when you will be rearranging V1, you will be getting it as root under 2gh into A2 square, and in denominator you will be having A1 square minus A2 square. So like for example, flow velocity we are able to calculate, but we are interested in finding out the volumetric flow rate here, which is v dv by dt, and you can also term it as q. So volumetric flow rate is going to be simply using principle of continuity, or simply we have already defined when we were discussing principle of continuity, it is going to be a1 v1. So this a1 multiplied with this term which we have already got is going to give you a1 a2 into root under 2gh upon a1 square minus a2 square. So this is one arrangement. Like you must realize, the another arrangement could be more appropriate to measure the gas volumetric flow rate using a Venturimeter, and that alternate arrangement is something like this. Let's draw this diagram. This arrangement is like this. And here mercury is filled in this connected two connected limbs. So now the idea is same. So here, say cross-sectional area is A1, cross-sectional area is A2. Let's say flow velocity is V1, flow velocity is V2 over here. So you can definitely see that A1 is greater than A2. So V1 would be less than V2. So P1 would be greater than P2. And we basically are looking to find out this quantity P1 minus P2. So if P1 is greater, so that is going to push the liquid here. Let's say the liquid here more, and this liquid this gas is going to push the liquid less, so the height of so pushing is less here, pushing is more over here, so this height will be more, this height would be less, and let's say this is the mercury. Okay, that is a rho hg, and the venturimeter measures this height h for us. So in order to have this relationship P1 minus P2, like in case of Pitot tube I already mentioned, that is going to be rho hg into g into h, that is in case of gas. Okay, and if that is liquid, okay, so that term will be rho hg minus rho into g into h, that is in case of liquid. Okay, and using Bernoullis principle, this P1 minus P2 term is gonna be equal to half rho V2 square minus V1 square term, and this would be equated to either rho Hg into G into H, or it would be equated to rho Hg minus rho into G into H, depending upon what is flowing in this pipe over here. So just by solving, you will be getting the different values of V1 and V2 over here. Okay, so let's write for in case of liquid, because in case of liquid, if you want to convert into the case of gas, you just have to substitute the value of rho as equal to 0 in this expression over here. So this term, like you are going to get, simply first of all solving this, you will be able to get V1 from here, and when you will be substituting the value in this, like Q is equal to A1 V1, so you will be getting A1 A2 multiplied with rho Hg minus rho upon rho into 2gh divided by a1 square minus a2 square. Okay, so you can observe the change, and like in the previous venturimeter, this term was not there. Okay, but in this inverted venturimeter, this term is over here. So this is the concept of venturimeter and how you are going to use um, it for the calculation of the volumetric flow rate of a liquid or gas in a pipe. Okay, so this was all about today. In tomorrow class, we are going to look at some more application. Okay, so and this is the end of the class today, and um, thank you very much for